somewhere in the Pacific Ocean right now. There is a steel box the size of a truck drifting just below the surface. It is invisible from a ship's bridge. It does not show up on radar. It sits at exactly the depth where a hull moving at 20 knots will hit it before anyone knows it is there. Inside that box, there might be furniture, electronics, running shoes, car parts, or chemicals. It does not matter what is inside. What matters is that it is out there, and it is not alone. The International Maritime Organization estimates that somewhere between 10,000 and 24,000 shipping containers enter the ocean every single year. The most commonly cited number, the one that shows up in maritime safety reports and naval incident records, is around 11,000. That works out to roughly 30 containers a day, one every 48 minutes, around the clock, 365 days a year. They fall off ships, they sink, they drift, and most of them are never recovered. The ocean floor at major shipping lanes is littered with them. This is not a freak occurrence. It is not a problem that is getting better. And the reasons it happens are a direct consequence of how the global shipping industry operates, how ships are designed, how cargo is loaded, and how the economics of moving freight across the ocean have created a system where a certain volume of loss is simply built into the cost of doing business. A modern container ship is an engineering achievement that is almost impossible to fully comprehend until you are standing next to one. The largest vessels in service today, the ultra-large container ships operated by lines like Evergreen, MSC, and COSCO, are over 400 meters long. They carry between 20,000 and 24,000 containers stacked up to 10 boxes high above the deck, with more in the hold below. The total weight of cargo on a fully loaded ship of this class runs into hundreds of thousands of tons. These ships do not stop quickly. They do not maneuver easily, and when they move through heavy weather, the forces acting on the cargo stacked on their decks are enormous. The physics of container loss is not complicated. A ship in rough seas pitches and rolls. The containers stacked on deck, secured with lashing rods and twist locks, are subject to acceleration forces that multiply with height. A container at the top of a 10-high stack is experiencing significantly more lateral force than the one at the bottom. When a ship encounters a wave sequence that exceeds the design parameters of the securing system, or when the lashing equipment is worn, improperly applied, or rated for lighter loads than the containers it is holding, the stack fails. It does not always go overboard all at once. Sometimes one container shifts, destabilizes the stack above it, and sends several boxes into the water in a cascade. Sometimes a single container goes quietly over the side in the middle of the night with no one watching. The weather dimension of this problem is significant and getting worse. Shipping routes cross some of the most consistently violent ocean on the planet. The North Pacific, the route between Asia and the west coast of North America, is subject to storm systems that generate wave heights above 15 meters with regularity during winter months. The North Atlantic is comparable. The ships that traverse these routes are built to handle severe weather, but built to handle and routinely surviving are two different standards, and the margins between them are where the containers go. The industry has known about the weather problem for decades. The response has been a combination of improved lashing standards, better forecasting technology that allows ships to route around the worst conditions, and the development of more sophisticated securing hardware. None of it has brought the loss numbers down to zero because the fundamental tension in the system has not changed. Moving cargo fast across the ocean is profitable. Slowing down to reduce rolling motion in heavy weather costs, fuel, and time. Spending more on lashing equipment and inspection cuts margins. The incentives point in one direction and the containers point in another. There is also a problem that is less visible than the weather, and arguably more consequential. Misdeclaration. A significant percentage of the containers that go overboard are heavier than their paperwork says they are. The weight of a container determines where it gets placed in the load plan, how it affects the ship's stability calculations, and what kind of securing hardware is used. A container declared at 20 tons that actually weighs 30 tons behaves differently in a seaway. It has more momentum, exerts more force on its lashings, and interacts differently with the containers around it. When enough misdeclared heavy containers are loaded into the upper tiers of a stack, the securing system that was calculated for the declared weights fails under conditions it was never actually designed to handle. The M.V. Deneb case in 2011 illustrated this precisely. The ship lost 18 containers off the coast of Spain during a storm, and the subsequent investigation found that multiple containers in the affected stacks had been significantly misdeclared by weight. This was not exceptional. Industry surveys conducted in subsequent years found that misdeclaration rates for container weight ran between 10 and 15% on major trade routes. The International Maritime Organization moved to make verified gross mass mandatory for all containers, a regulation that came into force in 2016. Compliance has improved the situation, but has not resolved it. Verification systems vary in quality across different ports, and the economic incentive to understate weight has not disappeared. Once a container is in the ocean, the Navy and the maritime safety community face a problem that has no clean solution. A container that is fully waterlogged sinks, which removes it from the surface hazard category, but creates a navigation hazard on the seafloor in shallow coastal areas and a pollution hazard everywhere. A container that retains air, particularly one carrying lower density goods or one with sealed air pockets, may drift just below the surface for weeks or months, at exactly the depth where it is most dangerous to vessels and least visible to surveillance systems. Some containers have been tracked drifting for over a year before sinking. The detection problem is real, and it is something naval architects and maritime safety engineers have not solved despite decades of effort. Radar does not reliably detect a low-lying metal object in a sea state that itself produces significant radar returns. Lookouts cannot see a semi-submerged container at night or in poor visibility. The AIS tracking system that monitors vessel movements has no equivalent for floating debris. When a naval vessel or a merchant ship hits a container, the incident report goes into a database. The damage is assessed, and the ship continues. The container is not recovered. Its location is not known. The database grows larger every year. The environmental dimension of the problem runs parallel to the navigational one. A container loaded with hazardous materials, with lithium batteries, with industrial chemicals, with pesticides, represents an uncontrolled release of those materials into the marine environment when it fails in the ocean. The cargo manifest system that is supposed to track what is in every container has the same misdeclaration problem as the weight system. Containers with undeclared hazardous contents have been documented in multiple loss events, and the ecological consequences of a container load of improperly declared chemicals dissolving into a section of ocean over a period of months are not cataloged with any precision, because no one is watching when it happens. The scale of the infrastructure behind all of this is worth holding in mind when considering why the problem persists. Global container shipping moves over 90% of all traded goods. The industry operates over 50,000 vessels. The volume of containers in circulation at any given moment is measured in the tens of millions. In that context, 11,000 containers a year is a fraction of a percent of total throughput. It is a loss rate that the industry's financial models accommodate without difficulty. The ships that lose containers are not penalized in ways that change the calculation. The cargo is insured. The loss is absorbed. The next ship loads the next stack and heads out across the same ocean. That is why 11,000 containers a year go into the ocean. Not because the problem is technically unsolvable, but because the cost of solving it completely is higher than the cost of losing them. The math has been done. The containers keep falling, and somewhere in the Pacific right now, one of them is drifting just below the surface, waiting.